Okay, I'm now wanting to talk about partial and semi-partial correlations, and those are basically ways to visualize the intercorrelation between both predictors and the outcome. And we're going to talk about two different types, partial correlations versus semi-partial correlations. Also, I want to talk about another issue that occurs when we're creating multiple regression models, multiple predictors on a single outcome. Then, just like multicollinearity, there's an additional problem that we have to look out for, which is called a suppressor variable, and I want to go over that as well. So when we're looking at even the simplest of multiple regression equations, we're basically talking about two predictors, in this case x1 and x2, and the actual outcome that we're predicting, the dv, y. And this interrelation between just three variables, let alone more complex models where there might be 5, 6, 7 predictors, creates a fair amount of options of what to look at when we're trying to describe how the variance is being partialed or assigned to variables. So for instance, if all we're interested in is the unique variance explained in our outcome by x1, that's A. And if we're only interested in the unique variance explained in our outcome y by x2, that's C. If we're interested in the total variance explained in our outcome y by x2, that's B and C. And likewise, total variance explained by x1 in our predicted outcome y is A and B. B represents basically variance that may be assigned to either x1 or x2 depending on the type of model and the order that we put these variables into the prediction matrix. The F boxes, or F sections, are basically representing the parts of both predictor 1 and 2 that are unrelated to anything else in the model, just like E represents the amount of variance in Y that is unexplained by any other predictors in the model. And finally, D represents the actual unique variance that is explained in predictor 1 and 2 that is not related to the outcome Y. And that D box, or D space, by the way, is what we're worried. If it's too big, that's where we start to look at multicollinearity issues. So if we're wanting to kind of talk about the types of variance that's being explained, we can talk about it in two different ways. And the best way to look at it is to continue with this example with our lettered boxes. And what we're basically looking at here at this point is either a semi-partial or part correlation or a partial correlation. I'm going to start on the right here with the partial correlation. The partial correlation is looking at unique variance in both the predictor and the outcome. So what we're looking for when we're actually calculating a partial correlation is we're wanting to know how much variance is uniquely explained from one predictor to variance that is not explained by any other predictor in our outcome. So in this case, what we're looking at is the amount of variance of A divided by the amount of variance in A and E. In other words, what is the unique variance explained by commitment on unexplained variance in years of marriage? So again, if there's variance in years of marriage that's being explained either possibly by either variable or possibly another variable, we're removing all of that. So a partial correlation is only looking at the unique variance explained by a predictor in the combination of that unique variance and unexplained variance in the outcome. A semi-partial or part correlation is looking at the unique variance explained in the total variance of our outcome. So in this case with commitment, A is the unique variance explained in years of marriage, and we're going to divide that by all the variance in years of marriage, which in this case is A, B, C, and E. So again, this one includes variance that's being explained by others, but is again looking at what is the partial explanation, semi-partial explanation of commitment on that overall variance. So just to kind of put that into words, a semi-partial correlation or part correlation estimates the unique combination of the predictor to the total variance of the outcome. So unique combination, contribution of a single predictor to the total variance in the outcome. Contribution of other predictors is removed from predictor 1, but it is still included in the total variance. So how this is often referred to is the R of Y predictor, 1.2 squared, is the proportionate total variance in the DV uniquely contributed by the RV. And you can actually get the R's, or the R squares of each of these proportional variables by going through SPSS readouts if you actually wanted to calculate this. By comparison, partial correlations estimate the unique contribution of predictors to the unexplained variance of the outcome. The contribution of the predictor is removed from the outcome and the predictor 1. So any other predictors is removed from the outcome, and any other predictors are removed from predictor 1. All we care about is unique variance in the outcome predictor 1 is explaining, and unique variance in the outcome that is not explained by any predictors. And again, this can be calculated by actually finding all of the individual R squares to run through this equation if you so wanted to. The suppressor variable problem is, again, it's similar to what's occurring with multiclinearity, but from a very different viewpoint. So with multiclinearity, the problem we have is two predictors are highly related to each other and highly related to the outcome. So much so that depending on the order they're put in and depending on how error is being assigned by the actual equations of the multiple regression, we may get some very different results from model to model. A suppressor variable is a little different because what this represents is there is a strong correlation between two predictors, and one of those predictors is not related to the outcome. So again, I have an example here where we have on our outcome years of marriage. We have a predictor, X1, commitment, that is related. So how committed you are does affect how long you stay married. So our commitment variable predicts A in the total variance of years of marriage, A and E. However, we also have a second predictor that we've put in the model that is absolutely not related to years of marriage, education, X2, but is related to commitment. So the more committed you are, the more education you get. Now what can happen here with the suppressor variable is two different things can happen. Now again, this is a static picture, but remember that when we're calculating any statistical technique, we are including basically estimates of error or variance. In other words, F may be more related to years of marriage than we think. It may be less related to years of marriage than we think. It may be less related to education. It may be more related to education. The problem here is that the equation has to settle on where it's going to put F. And if it decides to go moving more towards education as where that unexplained error variance should go, that actually might pull commitment out of being a predictor of years of marriage, even though it is. So again, we're looking at, in reality, it is a relationship between years of marriage and commitment. And a lot of times how we can find suppressor variables is, again, looking at simple correlations. So if we run a simple correlation of years of marriage and commitment and find that they're significantly related, and we run a single correlation between commitment and education and find that they are significantly related, and we run a single correlation between years of marriage and education and find they are not related. So now we know what they are in isolation. If we then put them all in the model and suddenly find that education becomes related to years of marriage, that means that it's probably a suppressor variable. Once you put all three in the model, suddenly the model is trying to drag education more into commitment, which makes it then overlap with years of marriage, which is not the actual case. Likewise, if we ran a multiple regression model with all three of the predictors, and suddenly we find that neither commitment or education is related to years of marriage, that's another indication of a suppressor variable. What has happened is that in the overall model, that error has been thrown more towards the relationship between X1 and X2, reducing the estimate of the relationship between X1 and years of marriage. Again, there's no easy test for a suppressor variable other than it's one of the reasons when we run a multiple regression, especially if we have a lot of predictors, one of the first things we'll do is simply run a correlation matrix which shows the unique bivariate correlations between every single predictor in our model. And again, a bivariate correlation just means a correlation between two variables. So it'll just give us a big table of what is the unique combinations of correlations between every single variable. And that way we can take a look and go, okay, we know what our outcome is, years of marriage. In the bivariate correlations, how many of these actually were related uniquely, individually, to years of marriage? Okay, if 4 of them are related and 2 of them are not, when we actually run our models, if we find that certain variables are no longer related, that might be an indication of suppression. Now remember that it might also be an indication of multiclinearity. It may also be a case where it's simply referring to the fact that 2 variables predicted a similar portion of years of marriage, and you don't need both to predict. So it is a bit of detective work to look for suppressor variables. But again, when you find a situation where suddenly in a simpler model like this, you have something that was predicting and no longer is for no particular reason. In other words, another predictor isn't now explaining that variance. It's just it originally was correlated with it, and once you put in this variable that's related to the other predictor but not related to the outcome, it suddenly now is no longer showing as related at all. That would be an indication of suppressing. In other words, education suppresses the ability of multiple regression to find the relationship that truly exists between commitment and years of marriage. So suppressor variables do not directly correlate with the outcome. That's our first clue. So if we have a variable that is a predictor but is not related to the outcome, again looking at just bivariate correlations. So for example, education is not related to years of marriage. And then, second step, we find there's a strong relationship with one of our other predictors with that outcome. So, for example, a strong correlation with other predictors may make suppression appear related to that outcome. So the next thing we're looking at is basically commitment is related to years of marriage. So it is related. It is not, education is not related to years of marriage. But if we have education and commitment in the same block or in the same model, does commitment suddenly disappear as a predictor? So when the regression includes both predictors, that may suggest that either both are significant suddenly or that neither are significant. So again, what suppression can do is it can either artificially inflate the suppressor to being related when it isn't, or the suppressor can create a situation where the predictor that should be related is no longer seen as being related.